Welcome to the second video of What Should I Watch While Eating series. Look up at the night sky. The stars seem scattered across a vast, empty canvas, twinkling like distant beacons in the dark. We perceive a universe of immense distances, a cosmic stage set in 3 dimensions, stretching out infinitely in all directions. But what if our senses deceive us? What if the reality we see is just a fraction of what truly exists? What if the universe holds more than meets the eye? More than our limited senses can detect? The quest to understand the fundamental nature of reality has led physicists to explore the mind-bending concept of extra dimensions, realms beyond our everyday perception. These dimensions could be hidden, folded into the very fabric of our universe. Imagine a tightrope walker gracefully moving across a high wire, balancing with precision. From our perspective, the acrobat exists in a one-dimensional world, confined to the line of the rope, moving only forward or backward. But an ant crawling along that same rope experiences a different reality, one that includes more possibilities. The ant can move forward and backward, but it can also circle the rope's circumference, experiencing an extra dimension hidden from the tightrope walker. This additional movement reveals a new layer of reality. This analogy, while simplistic, hints at the possibility of dimensions beyond our immediate awareness. Dimensions that could be intertwined with our own, yet remain unseen. Could our universe be like that rope, harboring hidden dimensions beyond our perception, dimensions that we are yet to discover? The answer, according to some of the most groundbreaking theories in physics, is a resounding yes. These theories suggest that our universe is far more complex than we can imagine. Our journey into the realm of extra dimensions begins with the familiar 4-length width, height, and time. But what lies beyond these? The exploration continues, pushing the boundaries of our understanding. We experience the world in 3 spatial dimensions. A box, for example, has length, width, and height. These dimensions define its position and allow it to exist within the framework of space as we understand it. But our universe encompasses more than just spatial extent, it also unfolds across time. Time, the 4th dimension, adds a crucial element to our understanding of the cosmos. We don't perceive time in the same way we perceive the 3 spatial dimensions. We can't move freely through it like we can walk across a room. Instead, time flows in a single direction, carrying us along from one moment to the next. For centuries, physicists viewed space and time as separate and distinct entities. Space was the unchanging backdrop against which the drama of the universe unfolded, while time marched forward at a constant rate. This classical view of the cosmos, however, underwent a profound transformation with the arrival of Albert Einstein and his groundbreaking theory of general relativity. In 1915, Albert Einstein unveiled his masterpiece, the general theory of relativity. This revolutionary theory reshaped our understanding of gravity, not as a force acting across space, but as a consequence of the curvature of space-time itself. Einstein proposed that massive objects like stars and planets create distortions in the fabric of space-time. Imagine a bowling ball placed on a trampoline. The ball's weight causes the trampoline's surface to sag, creating a curvature around the object. Similarly, massive objects create dents in space-time, and it's these warps that we experience as gravity. General relativity shattered the classical view of space and time as separate entities. Instead, Einstein showed that they are inextricably linked, forming a unified fabric space-time that can be stretched, compressed, and warped by the presence of matter and energy. This revolutionary insight laid the groundwork for exploring the possibility of dimensions beyond the familiar 4. In the 1960s, a radical new theory emerged from the realm of theoretical physics: string theory. This theory sought to unify all the fundamental forces of nature and provide a complete description of the universe at its most fundamental level. String theory proposes that the fundamental building blocks of the universe are not point-like particles, as in traditional physics, but tiny, vibrating strings. These strings are incredibly small, far smaller than anything we can currently observe, with even our most powerful instruments. One of the most intriguing aspects of string theory is its requirement for extra spatial dimensions. While we perceive only 3 spatial dimensions, string theory suggests that the universe actually contains 6 more. A total of 9 spatial dimensions, plus the dimension of time, making 10 dimensions in all. But if string theory is correct, why don't we experience these extra dimensions? Why do we perceive a universe of only 3 spatial dimensions? The answer, according to string theory, lies in the concept of compactification. Imagine a garden hose stretched out across a lawn. From a distance, the hose appears as a one-dimensional object, a long, thin line. But upon closer inspection, we see that the hose has a second dimension, its circumference curled up tightly. String theory proposes that the extra 6 spatial dimensions are compactified in a similar way. These dimensions are curled up on themselves at an incredibly small scale, far too small for us to detect with our current technology. Just like the ant on the rope, we are oblivious to these hidden dimensions, confined to our 3-dimensional slice of a much richer reality. In the mid-1990s, a remarkable development in string theory known as the second superstring revolution led to the emergence of M-theory. This theory took string theory to new heights, suggesting that the 5 seemingly distinct string theories were actually different facets of a single, more fundamental 11-dimensional theory. M-theory proposes that the universe is not made up of just strings, but also of higher-dimensional objects known as branes. These branes can have any number of dimensions, from 2-dimensional membranes to higher-dimensional entities that defy easy visualization. The concept of branes has profound implications for our understanding of the universe. Some physicists believe that our entire 4-dimensional universe might reside on a vast, higher-dimensional brane floating within an even grander multiverse. One of the most intriguing implications of M-theory is its potential to provide new insights into the origins of the universe. According to one scenario, our universe was born from a cataclysmic collision between 2 branes in the distant past. Imagine 2 sheets of paper floating in space. These sheets represent 2 branes existing within a higher dimensional realm. Now imagine these branes colliding. The impact would release an unimaginable amount of energy, potentially triggering the expansion of space and the formation of the matter and energy that make up our universe. This brane collision model offers a compelling alternative to the traditional Big Bang theory, potentially explaining the incredible energy and expansion observed in the early universe as echoes of this primordial clash of branes. Exploring the realm of 26 dimensions? While M-theory suggests a universe of 11 dimensions, some theoretical frameworks venture even further into the realm of extra dimensions. One such framework, known as bosonic string theory, proposes a universe of a staggering 26 dimensions. However, bosonic string theory faces significant challenges, including the prediction of particles called tachyons, which would travel faster than light, violating fundamental principles of physics as we understand them. While bosonic string theory remains a speculative area of research, it highlights the ongoing quest to explore the full spectrum of possible dimensions that might shape the very fabric of our universe. The concept of extra dimensions is undoubtedly mind-boggling, but it's important to remember that these theories are based on rigorous mathematical frameworks and are supported by a growing body of evidence. These frameworks are not just abstract ideas, they are built upon decades of research and mathematical consistency. Physicists are actively searching for experimental verification of extra dimensions, hoping to find clues hidden within the fabric of our universe. This search involves a variety of sophisticated experiments and cutting-edge technology, pushing the boundaries of what we know. One avenue of exploration is the search for tiny black holes at the Large Hadron Collider, the world's most powerful particle accelerator. This facility allows scientists to recreate conditions similar to those just after the Big Bang. According to some theories, the LHC might be powerful enough to create microscopic black holes if extra dimensions exist. These black holes would be incredibly small, but their creation would be a groundbreaking discovery. These black holes would evaporate almost instantly, but they would leave behind a telltale signature of particles that physicists are actively searching for. Detecting these signatures would provide compelling evidence for the existence of extra dimensions. Another promising area of research involves the study of gravitational waves, ripples in space-time caused by the acceleration of massive objects. These waves were first directly detected in 2015, opening a new window into the universe. By studying the properties of these waves, physicists hope to find subtle deviations from the predictions of general relativity, which could provide evidence for the existence of extra dimensions. Such deviations would revolutionize our understanding of the universe and potentially confirm theories that have long been considered speculative. The quest to understand the dimensions of our universe is a journey into the very heart of reality. It is a voyage that takes us beyond the familiar, into realms that challenge our very perception of existence. The theories we've explored, from Einstein's groundbreaking concept of space-time, which revolutionized our understanding of gravity and the fabric of the cosmos, to the mind-bending landscapes of string theory, which proposes that the fundamental particles are not points, but tiny vibrating strings, and M-theory, which unifies the 5 different string theories into a single framework, represent humanity's ongoing effort to unravel the deepest mysteries of the cosmos. While the concept of extra dimensions might seem like something out of science fiction, with its fantastical implications, it is a realm of active scientific inquiry, supported by rigorous mathematical frameworks and theoretical models, and driven by the search for experimental verification. Scientists around the world are using advanced technology, such as particle accelerators, to test these theories. The universe, as we are coming to understand it, might be far stranger and more wondrous than anything we could have ever imagined. It is a place where the boundaries of reality are constantly being pushed and redefined. As we continue to probe the boundaries of our knowledge, exploring the vastness of space and the intricacies of the subatomic world, we may one day find ourselves peering into those hidden dimensions, uncovering secrets that have eluded us for centuries, glimpsing a reality far richer and more complex than the 4 dimensions we experience every day. This new understanding could revolutionize our view of the universe and our place within it. The journey to unravel the true nature of our universe has just begun. With each discovery, we move closer to understanding the profound and intricate tapestry of reality. Please subscribe for more cosmic wonders.